the best university in China, where his PhD dissertation won Best 1000 Dissertation Award in 2006, the most distinguished award a PhD dissertation can win. He is currently an associate professor with UT, and he's an NSF Career Award winner. So he was a project manager in grid operation and planning at Palo Alto, California from 2007 and 2012. Now let's welcome Dr. Kai Sun for the talk.
Thank you for the introduction. It's my honor to give this first talk of this SLC seminar series. So I want to share something we did recently, which is very exciting to me. So I call it nonlinear modal decoupling. And if you Google this term, you won't be able to see this term before. So we try to make this term. And I will explain why this is really important to us, and especially for power system. I believe this idea is also valuable to more general nonlinear dynamic system and other fields. Today's seminar is more especially on the power system, but I would say more than 50% is about the general methodology. So if you're not in the power system background, you won't be able to feel anything that's not familiar. So actually, most of the material will be very general, and I believe you will feel this one interesting. Can you stay closer? Okay, good. And the content is, the first I will share some thoughts on understanding nonlinear electromechanical oscillation of power system. Maybe more general about nonlinearity in the oscillation, the more realistic oscillators. And then I will introduce the idea of a nonlinear modal decoupling. I will explain how that one can be applied to multi-merging system. And because my background is mainly in the stability dynamic study, I will utilize that idea to the stability study for power system. I will show some potential of this methodology. And most of the materials are based on the PhD work of Bin-Wang. Bin-Wang graduated in 2017, and now he's a postdoc researcher with the University of Texas A&M. Okay, so when we have a power system like this one, so it's actually a 39 bus system, 10 machine system, which represent a simplified system of the New England system. And it only consider 10 machines. And when the system has certain disturbance, and the disturbance usually here we consider large disturbance, and you will see the machine's angles will oscillate. And if the disturbance is too large, and some generator will diverge. So this one especially means this generator, and that model one power plant in Canada. If you have even bigger oscillation, bigger disturbance, you will see the entire group of generator will diverge, which represent this group of generators. Okay, so usually if we consider this power system as a nonlinear system, we will see the system just lose stability. Or maybe more rigorously speaking, there's a domain of attraction surrounding the equilibrium of the system, but because the energy of the system is too large, and the system will go outside of the domain of attraction, so it becomes unstable. So there's something we can observe. First is whenever there's a disturbance, and you will see those machines will oscillate, and they will have somehow periodical behavior. They will go coming back and forth in the angle, frequency. You actually can observe the oscillation from any data of the system, like voltage, current. And when the oscillation become growing, you will see all the generators tend to group. And for this case, there's a 3 groups, which really makes sense, because for this system, you will see there's a generation area, there's another area, and there's a power plant modeling the Canadian system. So they have a relatively weak connection between those 3 groups. And if you have some disturbance, for example, on that transmission corridor, and that generator will diverge. So for a networked system with a lot of oscillators, and if you have any disturbance, make the connection between any group of oscillator weak, and the system, one group may diverge, and that's how the instability may happen. This represents another scenario. And when we analyze this system, and we can consider an analogy, which is this system. So there's a lot of pendulars, lot of waves. They're connected by rubber band, and each wave may represent one generator. So that one can oscillate if you have any disturbance. If nothing happens, all the waves will stay there, stationary. So which is usually referred to the steady state condition in power system, or maybe in any other dynamic system. But if something happens, let's say if you cut one rubber band, and they will split into two groups and oscillate against each other. And for example, if you cut this rubber band, they will split two groups, which is very similar to this scenario. Okay, and to study stability of such system, if you refer to more general nonlinear system, you will see this is first is an n-body problem, which means for this case involve 10 machines. I have 10 bodies, and for such system, it's very hard to analyze. Okay, but as a power system engineer, you may feel that sometimes it's not exactly true, because for this case, if you know where how disturbance happen, the only scenario to call the system unstable is the system will split into two groups. Okay, if you can study the interaction between the two groups, you may have some method which is not 100% accurate, but still can help you detect the potential instability. So which means for this complex system, we may have some simple way to study its dynamics or its stability. Or maybe you can say the system has many different ways to oscillate, to change. But there may be just only one critical way, which is very important. If you capture that one, you actually understand the stability of this system. Okay, so this is the background of this research. Before we're talking about how to solve this problem, let's just go to a very simple oscillator. We start from the very simple one. This is a 1 degree of freedom oscillator, which is just a simple gravity pendulum. So you have a freeze point, and you have a rod, and connect a weight, or it could be a ball. And because it plays in the gravity, so the direction of gravity is downward. That's why. So this here is the equilibrium. So if you don't touch the ball, it will finally stay at the bottom point. That's the equilibrium. And if you have any disturbance, the angle this pendulum will deviate from the equilibrium. So you can use the theta to model that one. So my question is this system linear or nonlinear? Let's calculate the frequency for such system. If it oscillates, it will oscillate at a certain period. And if it's a linear system, the linear system only have clearly a number of frequency, and each of them are actually constant. That's how we call them a harmonic system. But if you calculate the frequency of this system, you can solve it because it's a very simple system. You can have a differential equation to model the motion of the pendulum, and the answer is this formula. So the period, oscillating period is this term multiplying a whole bunch of terms, infinite number of terms in the bracket. Okay, if you list maybe 1, 2, 3, 4, the first 4 terms, which will look like this one. This expression can be obtained by solving an elliptic integral with doable. You can just Google like a gravity pendulum. There will be a lot of documents giving you the same formula. So based on this formula, you can tell the frequency is actually depending on this angle difference. So if you give it the initial difference from the equilibrium, and that will change the frequency. So which means the system may not be exactly a linear system. Okay, but why do we usually consider a pendulum as a linear system? Because if this theta is very small, if this theta 0 is very small, all such sine theta can be simplified. Finally, what you get is only this one. So you only just have the first term, all the other terms are 0. So you have a linear pendulum or linear or harmonic oscillator. So for example, if this initial angle is less than 30 degrees and the period is very close to this formula, that is just first term. So you can treat such system as a linear harmonic oscillator. But the original system is not really a harmonic oscillator, it's a nonlinear oscillator. So for example, if you want to figure out how the frequency will change or the period will change by using many different terms. For example, you can calculate the period using just one term, two term, 5, or even 100,000 terms. So what you get is this chart, this figure. X is the initial angle difference. So where you release the ball, and it will start oscillate. And so you can see the blue one is actually the linear one, the first term. But when you submit the first 100,000 term, the period will grow with the initial, the period will grow with the initial angle deviation. So if you move the ball away from the equilibrium, and the frequency will, the period will increase, and this is show the frequency will drop. Okay, it seems from the chart, the period will increase infinity, which means the frequency will drop to 0. What does 0 mean? 0 just means the system has another equilibrium, which is different from the bottom position. That's an unstable equilibrium. So when the handler go to that unstable equilibrium, the definition of frequency is just lost. There's no such periodic dynamic anymore. The pendulum will just revolve in the same direction. Okay, there's no such periodical behavior. Okay, so that is pretty interesting. But why am I interested in this system? So let's generalize that pendular system. But what I did is just I added a constant torque. I call it a tau n. You don't need to worry about how I add this torque. It could be added on this pivot by whatever way, but that torque is constant. By adding that torque, if that torque is counterclockwise, you can tell the new equilibrium will not be the bottom point, it will be somewhere here, has certain angle which is delta x from the bottom point. So that is my new equilibrium. And if I try to list this differential equation, that's very simple. The equation is just like this one. You need to use the Newton's law. So you can easily get this differential equation. That's second order differential equation. And this explains why this one is nonlinear. Because there's a sine delta term here. That's not a delta. If you have a very small initial deviation, that sine delta will become delta. That becomes linear system. Downgrade to a linear system. Okay, so let's take a look at another system which most people here are very familiar with. Before that, I just try to generalize. I define the moment of inertia, and also this is I define maximal torque. Maximal torque happens when this pendulum moving to this position, and it has that will reach a maximal torque. So this is the second order differential equation, which is nonlinear. Let's take a look at this system, which is very familiar to us, right? That single machine infinity bar system. So here is the infinity bar. Infinity bar that represent the, it's not a load, it's an infinite system. It's a pretty large power network, such as that system has constant frequency and also constant voltage. And you have a single generator connected to that system through transmission line, maybe transformer, and the total readance is X sigma. So if you model this system, you can easily write down swing equation, which is this one. But you also can define the inertia. You define this part of the inertia, for example, and you also can define the maximum torque. Very interesting thing is it becomes the exactly same system. So for the simple gravity pendular, when you add a constant torque, that is equivalent to a single machine infinity bar system. Okay. So what is the infinity bus for this pendular system? The infinity bus is the Earth. Okay, that's why that makes a lot of sense. And in this case, the infinity bus is just another large system. So we don't care what it is. It's too large. It won't move and it won't change any voltage, any frequency. So we just need to study this system. So this system has 2 equilibrium points in 360 degrees. The first one is this one. The other one you can easily know that's a 180 degree minus delta S. So there are 2 equilibrium, and the first one is stable one, the other is unstable. I think many people already know this conclusion. Okay, then we start from this general equation. So from now, this equation represents both the pendular system and also single machine equilibrium system. So we want to even generalize this one. We define, for example, we divide both sides by I, by the moment of inertia. We get this equation. So it has a second order derivative, first order derivative with coefficient alpha, and this term, nonlinear term with beta. And this one that represents the equilibrium. And we have this equation. That's the same equation to both systems. And we can even really define the deviation of angle, deviation of the angle from the equilibrium, which is a delta delta. And that is this equation. So those 3 equations are completely equivalent to each other. There's no approximation and no simplification. They are representing exactly the same system. But if you look at this system, that's pretty interesting. It's very similar to a linear system, linear second order system, right? Because if you consider everything in this bracket to be a constant value, so this becomes a linear system. But because it's nonlinear, so this one change with the state variable, so it's not constant. But if we're pretty sure the system will deviate from the equilibrium at a very small scale, it doesn't change too far away from the equilibrium, we can assume the delta delta to be very small, let's say 5 degrees. Then this one will be constant, and it will downgrade to a linear system. So this is exactly the linearized system we have. So this is such a second order differential equation. Okay, so now give you one example. We just assume certain typical value which are typical for power system. The power system, this generator operates at 30 degrees, which is different from the infinity bus system. And we consider 2 cases. The first one, we add a very large disturbance. So how do we do that? We just give it an initial speed, which is very large. And so if you still remember the unstable equilibrium point, the unstable equilibrium point is equal to the 180 degree minus the stable equilibrium point. For this case, start from 30 degrees, so the unstable equilibrium point is 150 degrees. So you can tell it's almost reached that UEP, unstable equilibrium point, but didn't. So that is the stability boundary. So system is still stable. We call it a marginally stable system. And so if you draw the phase plot and about angle and also derivative by angle, so you can see it will finish a loop, and it will stay around this locus forever. Okay, if you don't have damping, if you have damping, finally it will go back to the equilibrium. So this is nonlinear oscillator. Another one case, you can try very small disturbance to give it very little speed. If you only just stay around within 60 degrees. Okay, so for this case, you can tell this one is very like a harmonic oscillation. And the frequency is almost equal to this value. And if you draw the phase locus, it's like that one. It's much smaller, but you can still tell the shape is not circle. It's very like circle, but it's still not circle. You can see the shape is the right side and this right part is different from the left part. And the observation from this case is compared to harmonic oscillator. And the waveform of such system is not symmetric. For this case, this part is bigger than the lower part. And the frequency actually decreases with the growth of amplitude. So when you increase amplitude, this is the same length of time window, you have fewer than 3 swings. But if you have a smaller amplitude, you have more swings. So which means frequency, this frequency is lower than that one when you have a higher amplitude. So maybe we can borrow a tool from that pendular system to study how the frequency will change with the increase of the amplitude. Okay, so we propose this one, we call it a frequency amplitude curve. It just defines how the oscillation frequency as a function of amplitude. That one can be solved. This one can be analytically solved. I just don't have space to show all the detail. You need to utilize the elliptic integral of the first kind, and you can have this analytical formula, which is it's analytical, but you have to consider many infinite number of terms to approach to this frequency, which is very similar to the pendular case. So if you draw such a frequency amplitude curve, X is oscillation amplitude, Y is oscillation frequency, and so there's a one point which indicates zero amplitude. So zero amplitude just means equilibrium. The system doesn't move. So this point is just a projection from the equilibrium. And they also have another point, we call it the nose point. So nose point indicate largest amplitude but the zero frequency, the loss of definition of frequency, which is the other equilibrium. That's unstable equilibrium. Okay, so if your system has certain disturbance, it will move. In the phase domain, it will have a phase locus, but in this domain, it always stay on this curve. Okay, so after some disturbance, it may move to this point. It will have this large of amplitude, and the frequency will drop from initial frequency, nature frequency of the linearized system to this lower value. But if you have damping, it finally will go back to the equilibrium. So actually, the distance between the lowest frequency point you can reach between the nose point actually tell you the margin of stability. So we can define that one to be stability margin. Okay, so for such nonlinear oscillator, you can analytically solve such a curve, and if the system is too complex, and the theory tell you it's still somehow such a curve. Okay, so when the system reaches the unstable equilibrium point, and the frequency will lose its definition, so it will go to some nose point. And you can use data-driven approach to try to fit such a curve. That's doable. Once you have this curve, all the system behavior will become monotonic on this curve, so which is very easy to analyze the margin of stability. So there's more detail on that paper if you have interest in this work. So how about the multi-machine system? And all the previous cases studies about a single pendulum. A single pendulum versus the Earth is actually two-body system. A single machine infinite bar system is also two-body system. But if we add another machine, so we have a three-machine system become a three-body problem. So is the FA curve still true for such system? We can consider disturbance, which is a short circuit here by opening the line. And if you do the time domain simulation, you will see angle of three machine will oscillate in such way. And we use one as a reference. We use machine number one as a reference. That's why that one is zero. The other two will change. And we define different time window. So for each time window, we try to study how the system trajectory will change. And we pick one domain. The first domain is, because this system is actually a five-dimensional system. It's a three-body system. Each machine has a two state variable, which is six-dimensional nonlinear system. If you use one angle as a reference, you can eliminate one dimension. You have five dimensions. You have five dimensions, so it's a five-dimensional nonlinear system. And you can also define, let's say, all the damping of such system is uniformly distributed among the generator, which is proportional to the inertia. You can also cut another one dimension. So you can simplify such system into a four-dimensional nonlinear system. So for the four-dimensional state space, if you want to visualize the trajectory, you have to, in the two-dimensional plan, you have to pick any two dimensions. For example, we pick this is one dimension, this is another dimension, and this is ICP, that's stable equilibrium. And you also have unstable equilibrium. And the stability boundary is somehow here. And after you have that fault happen, and the trajectory will jump to some point very close to the boundary. But fortunately, the system is not unstable. So we'll come back. Finally, it will go back to the equilibrium. And those P1, P2, P3 are basically talking about the trajectory coming from the different temperatures. This is one way to visualize. Another way is, if you're lucky, you may choose this visualization, which look much clearer than this one. This is like a fuzzy, right? You don't understand what is happening on the system. But for this one, because you choose a better coordinate to visualize the system, you can tell. So after disturbance, it will jump to a point which is very close to the UEP, and finally, it will go back to the equilibrium. Okay, so for such complex system, if you use traditional way to analyze the dynamic in the higher dimensional space, how easily you can obtain the result really depends on which coordinate you want to choose. So if you choose the wrong coordinate, and finally it's very hard to get useful information. But you can also try to generate an FA curve. The FA curve also shows it's also always monotonically changing. If you have a disturbance, it will move to this point. And finally, it will come back to the stable equilibrium point. So the FA curve gave you a clear display on what the system what's happening on the system. So to explain why the system may have a lot of chaos before coming back to the equilibrium. And this is an analogy. It's not very accurate, but it just gives you some idea. And for the linear system, you can think about that linear system, the manifold is somehow in the linear, which is hyperplane. So this is blue one. But when the system becomes nonlinear, the manifold will be this concave surface. Okay, so it's a tangent to that hyperplane only at the equilibrium. Because this surface is concave, and also this manifold may have some saddle point. The saddle point does indicate that unstable equilibrium point. Okay. So that's why when the equilibrium deviates from the bottom, and the frequency will change, and the system will be not like the harmonic oscillator anymore. So how about the even larger system? So let's consider the 179 bar system. This one is a simplified version of the Western connection. And we simulated some events very similar to the West Coast blackout in 1996. There's a lot of disturbances happening on the California-Oregon intertie to cause the separation of the two areas. If you keep adding the disturbance, you will see the oscillation will grow. This represents the angle difference between the two areas. And you can tell actually the waveform is pretty clean. So which means there's one oscillation mode dominating the system oscillation. That mode is about 0.2 Hertz. And if we especially interested in that mode, we can draw this FA curve. And after the first event, so that's only part of the FA curve. So the system state doesn't go too far away from the equilibrium. So that's why it's very short FA curve. But when you keep adding the disturbance, finally, the largest one before system loses stability, and that almost give you the entire FA curve. Actually, the system reached this point, which is less than 30% of the market to the instability. So how about the other oscillation mode? You can actually draw the FA curve for every dominant oscillation mode. Because the system is too complex, it's not very easy to derive the formula for FA curve. But you can try a data-driven approach. You can try to energize only one specific mode, and you will see the way the system will have that oscillation. And using the data, you can actually draw those FA curves. So this could be some idea which can generalize to multi-machine or n-body system. Okay, so that's almost the first topic. And the second topic is some thinking following this first topic. Okay, let's think about the n-machine power system. So if we do the small disturbance analysis, which means we only have very small disturbance, such as the system can be linearized, like this one, that's a linear system. And for linear system, we can always do linear modal decomposition. So rigorously speaking, all the eigenvalues should be different. They shouldn't have the same eigenvalue. Okay, we can do some linear model decomposition by introducing some orthogonal matrix where actually we can decompose, transform the original system to a new system. So in the new system, this lambda is actually the diagonal matrix. So actually decompose all the mode. So each mode is represented by only with a single state variable of the new system and related to a lambda eigenvalue. So that eigenvalue, the real part is damping, the imaginary part represents the frequency. So this is linear system. So such as for linear system, if you're oscillating, we don't worry too much. No matter how large the system is, we only just need to identify which eigenvalue is very critical. That is very close to the imaginary axis, right? We try to do some control to improve the damping part, and the system can be damped. So no matter how large the system is, but for nonlinear system, it's a completely different story. There's no such model decomposition. Okay. If under large disturbance and the nonlinear system cannot be simplified as a linear system, but is there anything we can do? For example, by introducing some coordinate transformation. So X is the original state variables in the power system, but we can define some new state variables, and which actually can be transformed from the original state space. Of course, this is a nonlinear transformation. It's not a linear transformation anymore. After this transformation, we have a new system. And the new system, the good thing with the new system is each state variable represents one oscillation mode. And it's not coupled with any others. Okay, you can tell. So this system the state variable is placed in a vector. So each element is fully dominated by a nonlinear system. It's still nonlinear, but it doesn't couple with any other oscillator. So can we do this? So if we can do this successfully, what that means for this multi-machine system, if this is the mode which is going to cause instability, we don't have to study original 10-machine system. We just need to study the system associated with this mode. That's very simple. Even that's a nonlinear, that's 1 degree of freedom. It's very similar to the pendular system. That can simplify your analysis, and you can even draw that curve representing that mode. Okay. So, but how can we do that? So which means we want to do somehow decoupling among those modes. That's a regional N-machine system or N-oscillator system. Actually, each one could be a nonlinear oscillator. They couple through the connection. For the power system, they couple through transmission line. For that pendular system, connected by rubber bands. This is a regional state space, which is X. And we want to introduce a new state space, which is Z. By introducing this nonlinear transformation, we decouple the regional system to many oscillators. The number is n-1. So why is this n-1? Because N-machine system has only n-1 degree of freedom. Because if you use one machine as a reference, where does the number n go? That one become a non-oscillatory mode here, but that it's not important to us. That is important to frequency control. For example, all your generator speed up from 60 Hertz to 62 Hertz. That is not secure in terms of frequency. But in all the generators still stable, they're still coherent with each other. So when we study stability, we don't really care. They're entirely going up or going down. So that is represented by this non-oscillator mode. And we have no interest regarding the rest of n-1 oscillators. How can we do that? And there's a hypothesis. So the dynamics of an N-machine system in the neighborhood of a validity region regarding the equilibrium can be decoupled into dynamics of n-1 nonlinear oscillators. And each oscillator is 1 degree of freedom system. This is what we get and also what we hope. Okay, and if there's such transformation, first of all, the transformation must be non-unique. Why? Because each decoupled oscillator depends on desired modal nonlinearity. So I will explain what it means, and also depend on the desired size of a validity region. So if you validity region is 0, which means for this decoupled system, which can be applied to a region of size of 0, which is just the equilibrium point. So this transformation will downgrade to linear transformation, will downgrade to the to diagonalization of the linear model of the system. But if you want a bigger region, and the transformation will be more complex. And for the desired modal nonlinearity, you may expect each oscillator will be exactly single machine infinity bar system. Why? Because you like a single machine infinity bar system. It's very easy to analyze. That's fine. Then you can derive that transformation. But if you give the system to some professor, for example, in the mechanical engineering, they don't expect the decoupled system to be single machine infinity bar system. It can be anyone they can handle. Then you can define what that modal nonlinearity is. Okay, so can that one be done? The good news is, theoretically speaking, that is doable. That is because of this theory. This Poincaré's normal form theory. That is basically the core work of the dissertation of Poincaré. And what this theory is talking about is, if we consider smooth nonlinear system, which is like this one, I star equals fx, and f is a vector valued function, which means f is a vector. So each element is a function. The function has to be smooth. Smooth means this is is differentiable at any order, at any high order. So which means each element could be a polynomial function. The system can be written in such a way. It has a linear term, linear part, and x2 just means it's also a vector valued functions, and each function is a homogeneous polynomial of order 2. So x3 is the polynomial of order 3. Okay, so you can keep writing the term to cover all the orders. So if this is a system or original system, so if the eigenvalue of the matrix, the linear part, is non-resonant. So non-resonance means so none of the eigenvalue of the original system, the linear part, can be represented by the linear combination of other eigenvalues. Or they're completely irrelevant. So if there's no resonance, and the system can be reduced to a linear system. If we define the space of Y, and how do we do that? We can do that by a smooth coordinate transformation. We call it H. And by just plugging this one into the original system, and the function of H2, H3, each of them is still a homogeneous polynomial functions of a different order. Those will cancel F2, F3. And you will get this linear system. So that's a theoretically speaking, that's doable. And he even gave the this so-called homologic equation. The homologic equation is talking about the difference between the original system and target system is equal to the Lie derivative of that transformation, which is LA. If you don't know what the Lie derivative is, but you can tell that can be defined by this this equation, differential equation. Okay, so by using this, solving this differential equation, you can actually eliminate F2, F3, F4 one by one. Okay, this is the theory, and to serve our purpose, we want to decouple the complex multi-merging system into multiple systems, and we don't care whether each system, decoupled system, is linear or nonlinear. We don't have to reach to this stage. We only just want to have each decoupled system which is nonlinear but is not coupled with anything else. So, for example, this is our expectation. So you may still can have some different orders of nonlinearity. If that's the case, you just need to add those g's here. So this equation is still true. So the difference between the two systems can be solved by this differential equation. So that's a doable, theoretically speaking. And we just need to design the J2, J3 while to make those state variables be decoupled. Okay, so we propose this nonlinear mode decoupling idea, and this could be the final target of our decoupled system. And the first part is decoupled linear system. So lambda is a diagonal matrix of eigenvalues. And starting from the second order, you can see D2 until dk. Each term is only about one specific mode. It's not coupling more than one mode. For example, if one polynomial in this part, if Z1 is just single mode of mode number 1. So this D2 only just has Z1. It doesn't have Z2, Z3, Z4. And so those are completely decoupled up to case order. And the rest of it, I color them in red color, which could be decoupled at the k+1 order, or maybe still coupled. So which means each term here will involve Z1, Z2, Z3, multiple Z. Okay. The Poincare theory tells we can actually do this. Theoretically speaking, we can do that. And so we can think about this is just a method based on the Poincare theory. So how do we do that? We follow the same idea, which is a homologic equation. We can construct a transformation nonlinear, which is a sequence of homogeneous polynomials of different orders. So for example, X is our original one, Z is our target. Assume there are many different transformations together will transform Z back to X, transform the decoupled system, fully decoupled system back to the coupled original system. Go through a number of transformations. And if we apply the inverse transformation, for example, the first one, the H1, and so we actually transform the left-hand side to be, we call it Z1. Z1, based on our definition, is just decoupled system only up to the first order. Okay. So which means by applying those H1, H2, H3, you actually you gradually decouple the original system to the first order, second order, third order, until certain order you're pretty satisfied. So the order has been high enough. And the remaining part that is not decoupled is too small. The order is too high. So in the large enough validity region, and those remaining terms can be ignored. So actually you decouple the first k terms. And we call the summation of the first k term as a decoupled kz. So kz is approximation, but which is decoupled. So how about the desired model nonlinearity? So that mainly depends on how you can design those blue terms. We call it intramodal term. Intramodal just means it does only involve one mode. It doesn't involve multiple modes. So basically just the D term from D2 to DK. You can design those values. For example, simplest case, you design everyone to be 0. That's exactly the same as what Poincare proposed. That you transform the original nonlinear system to linear system, and linear system can be diagonalized, which means it can be linearly decomposed. Second one, you can assume each decoupled system is very like a single machine infinity bias system. And third one is maybe you can propose additional assumption. So this is assumption we propose as a comparison to the single machine infinity bias assumption. So this assumption says by applying those nonlinear transformation, we don't want to introduce additional term. So if original equation doesn't have such a term, We don't want to introduce a new term. We just make the expression as simple as possible. And we don't care they can approximate a single machine feedback system or not. We don't care, but we want the formula to be simple. Okay, so how does the nonlinear mode decoupling differ from a normal form, the classical normal form? The nonlinear mode decoupling only eliminates any nonlinear intermodal term whose order are lower than k. Right? But the normal form actually eliminates any nonlinear terms. So if this is a original system, and the normal form will have a linear part, and for the nonlinear part, the first nonlinear term only appears with order k plus 1. And for the nonlinear mode decoupling, we allow the system to have a many nonlinear term, as long as each of the terms only involve just a single mode. So if you draw the some analogies representing the three different systems, this is my original system. So there's a concave surface which is very irregular. And there's a ball moving around, and there's a boundary which represents the boundary of the stability or boundary of the domain of attraction. And the bottom is equilibrium. If you study such a system, and it could be very complex. The trajectory could be anyone within anything within this domain. And the normal form may try to regulate the surface in a shape which you like. For example, for a linear system, the shape will be a parabolic surface, which is very simple to study. And what nonlinear mode decoupling is doing is, for this two-dimensional surface, we decompose this one into two single-dimensional surfaces. So each one represents a single mode. And we can even design the shape of this surface. The good thing is the stability problem or dynamic made it happening on this mode, not the other mode. So this system state will stay at the equilibrium. So we'll not be able to observe dynamics on this decoupled system. We can only use this lower dimensional system to study the problem. Okay, so how much time I have? Okay, I quickly go through some power system example. This is a three-machine system. So in order to apply the approach, we use nonlinear mode decoupling. We get a Taylor series for each nonlinear function, which is Taylor expansion and approximation. We only do up to third order. And the first decoupled system is representing the desired modality, which is same as the single machine feedback system. The second is another one we try to compare with that. And this is normal form. You can tell this is a linear system. Okay. Then we compare the accuracy among those three decoupled systems. We check a small disturbance and large disturbance. For small disturbance, all decoupled systems are almost exactly the same as the original system. Original system here, the color is a green color, and the red indicates the single machine free bus assumption, and blue is the normal form assumption, and the black is another one we recommend. So all the three are the same, very close to the accurate one. But if you tell the error, you go into the details of the error, you can tell the single machine free bus system assumption has the largest error, even larger than the normal form result. The normal form is do a nonlinear transformation to change the regional system to a linear system. But by assuming the decoupled system still as power system, single machine feedback system, the error is even larger than that normal form. But when you have a large disturbance, you can tell the single machine feedback system assumption still has very large error. And now the normal form also has large error. And the other one, what we recommended as smallest error. And to show the system dynamic on the phase plot, that is the original phase plot in original space. After transformation, you can tell there's a two mode, right? The dynamics is mainly happening on the number two mode. But for the mode one, it's basically the dynamic is not very visible. It just stay around the equilibrium. So we successfully decouple the system dynamic. This gives you a better idea on what the manifold look like. The regional system dynamic stay within a fourth dimensional manifold. By the decoupling, we decouple regional fourth dimensional manifold into two-dimensional manifold. And each represent one mode. So for example, this represents the faster mode, the other represent another slower mode. And you can tell from this manifold, and the unstable equilibrium point is closer to the stable equilibrium point. That's why the system tend to become unstable regarding that mode, not the other mode. I want to skip this one. This is bigger system about the same result. Let's skip this one. I want to quickly talk about this result. This is a test on the MECZ large-scale system with 48 machines. We add some disturbance in the iso-England region. Although the entire system is oscillating, but if you check the oscillatory energy of different modes, you will tell there's many modes because there's 48 machines. And the top three modes are very critical. You can tell the largest mode takes 30% of oscillatory energy. The second takes 68%. And the third one takes 2%, almost 2%. And all the other modes together take less than 1%. So even the system is very complex, but the dynamic is mainly regarding three oscillation modes. And the mode number one is the oscillation across this boundary. And mode number two is the boundary here, and that is mode number three. And if we apply this approach, we can apply this approach for the mode number one and mode number two. And for each mode, the decoupled system is second-order system. So the boundary can be easily solved, which is those boundary. And after following disturbance, you can tell this mode has very large dynamics. And the system trajectory go outside the boundary for temporarily, but it will come back. And for the other mode, the equilibrium, the system dynamics stay within the boundary. Okay. So also tell the successful decoupling of the system. And also the boundary estimated for decoupled system is conservative, which means it's smaller than the accurate boundary. Okay. To summarize the findings from this work, first of all, so there's an equity curve. We can model the nonlinearity of the electric mechanical oscillation. It can describe how the frequency decreases with the increase of amplitude. It's a similar concept to the pivot curve of vortex-based stuff. The second one is the nonlinear mode decoupling, and using the conic transformation, you can decouple system. The most interesting thing is the decoupled system is not necessarily single machine feedback system. The single machine feedback system is not the best option. So this one may give you a theoretical evidence on some modal reduction. For example, you have many generators, and you can treat one group of generator as a single machine, the other group of generator as a second generator, and that simplification may not be accurate. Because that falls into the scenario here of a nonlinear mode decoupling, by which you assume the decoupled system to be single machine feedback system. Okay, so this is the last slide, and so this work is supported by the NSF and by CURENT and also by the career work. Any question?
How to calculate the modal energy?
Yeah, that is from the software. This is from the TSET. That's a pretty easy practice. Basically, you just estimate the amplitude. You decompose the signal into the signal at different frequencies, and the amplitude will tell you the modal energy.
Just explain the more transfer assumption in more details.
So no time. If you have interest, you take a look at the paper. And you should read the paper. Any other question?
So more energy means it's more likely to be like likely to have larger amplitude.
I didn't capture your first part.
Still regarding this modal energy.
Okay, yeah.
So more energy,
yeah.
what does it indicate?
Yeah, let's use this one as an example because this mode has the largest modal energy based on that study. That is just a linear probe. This is not nonlinear. This is from a commoditized product. Just do a single decomposition into many different frequencies. So I'm not sure those results are accurate. As I said, it's a nonlinear system, but still can somehow rank those modes by their amplitude.
Oh, so this is for specific the disturbance.
Yeah, the dispersion change. For example, you add dispersion here, that mode won't have a large energy.
Okay, I got it.
Yeah. So this one can tell clearly what's happening. It's happening even if you do simulation for the entire system, all the curves, you have to observe all the 48 machines, right? But this measure tell you the dynamics really happening on this specific mode. It's pretty close to the boundary. And even for the second mode, the rank number 2, which still have very large energy, but that is far away from the boundary.
Okay, if there is no more questions, please join me and thank Dr. Sun for a very